Welcome to a new video of heat transfer. Today we continue our discussion on the fundamentals of convection. In particular, we are discussing the velocity boundary layer, the thermal boundary layer, the Prandtl number, and the Reynolds number. So let's start to talk about the velocity boundary layer. So when we have a flow that runs past a flat plate, for example, a boundary layer, a velocity boundary layer develops near the surface. This is the region bounded by the surface where velocity gradients are important. So we called this thickness, so the distance from the wall where the velocity gradients are important, delta V. That's a boundary layer thickness. And there are different ways to define this thickness, but in our interest we can just define it as a location from the wall where the streamwise velocity u is equal to 99% of u infinity, where u infinity is the free stream velocity, so the velocity of the fluid at a large distance from the wall. So why does these velocity gradients occur? Because of the no-slip condition. If the plate is not moving, then the velocity of the fluid particle at the surface is also zero. So there is no slip, so there is no relative velocity between the plate and the fluid. Since the fluid is a continuum, then the velocity must increase from zero at the wall to the free stream value u infinity. So there must be a region from the wall to the free stream region where the velocity changes. So there's a velocity profile. And here we're only sketching the streamwise component of the velocity vector. So slightly more detail, we can define a coordinate system x, when x is the streamwise coordinate, so it runs downstream, and it's zero at the leading edge of a flat plate. And y is the wall normal coordinate, so it's zero at the surface of the wall and increases as we move away from the wall. So in the proximity of the leading edge, we have a laminar boundary layer, so the particles of the fluid slide smoothly one on top of each other, and there is no bulk motion, there is no vortices, so the motion of the fluid is very regular. Then eventually there are some sort of instabilities that develop for different reasons, for example, because of free stream vortical disturbances or roughness. And these instabilities can be of different kinds, called, for example, Tolmin-Schlichting waves or Klebanov modes. And so we have these sort of perturbations that kind of disrupt the smooth motion of the laminar boundary layer, and this is the transition region when the flow, as it evolves downstream, changes from the laminar to the turbulent regime. So further downstream, at the end of the transition region, we have a fully developed turbulent boundary layer, which is defined as the region where the flow is fully turbulent. So we can still define a thickness, thickness of the velocity boundary layer as distance from the wall, where the mean velocity now reaches 99% of the free stream velocity. And we observe that the thickness of the turbulent boundary layer is larger than laminar boundary layer, and so in general the boundary layer grows as we move downstream because viscous effects continue to diffuse. A very important concept when we study boundary layers is the wall shear stress. So here we have sketched again the velocity boundary layer, and so we remind ourselves that particles stick to the surface because of this no-slip condition. As we move away, then the particles start having larger and larger velocity as the free stream is approached. So we can think that these moving particles exert a force on the particle that stick at the surface. So we can schematically represent it here. So this is the particle near the surface, and this is the particle at the surface. The particle at the surface has zero velocity because the wall is not moving, it's no slip condition, and instead the velocity away from the wall has a certain, this particle has a certain velocity, so there is a force that exerted by these particles, and this is a local stress. So this local stress is felt at the wall. It's called wall shear stress. So this local wall shear stress, so it's a force that's parallel to the wall and is due to viscous effects. So viscosity is a property of the fluid and is measured by the dynamic viscosity indicated by the letter mu. So the units are kilogram divided by meter and times seconds, or Newton times seconds divided by meter squared, or by Pascal times seconds. So what's the mathematical formula for the wall shear stress? So the wall shear stress actually has a form, mathematical form, that's similar to the Fourier's law. So we indicate the wall shear stress by the letter tau with the subscript W for wall, equal to the dynamic viscosity times the gradient of the streamwise velocity with respect to y, evaluated at the surface y equals 0. And the units of the wall shear stress are newtons divided by meters squared. So I said that this formula is similar to the Fourier's law. So in the Fourier's law, we have here instead the magnitude of the heat flux along a certain direction, and here instead of mu, the dynamic viscosity, we have the thermal conductivity. Instead of the gradient of velocity in Fourier's law, we have the gradient of the temperature. So there's a strong analogy, although there is no minus sign in the case of the wall shear stress formula. So for fixed viscosity, the wall shear stress is larger if the gradient is, or the velocity is larger, and instead for a fixed gradient, the larger the viscosity, the larger the wall shear stress. So this form of relationship between the wall shear stress and the velocity gradient is typical of what we call Newtonian fluids. So these are the simplest fluids that we can find. For example, simple oils, but also air and water behave in this way. So let's go back to the case of the flat plate. So now, if we integrate the wall shear stress over the surface, then we find the friction drag force. So we recall that the units of the wall shear stress is Newton divided by meter squared. So if we integrate over the area, we find Newton, we find a force. So this is the aerodynamic drag over aircraft, cars, ships, and so on. Or it can be interpreted, for example, in a wind tunnel, as the force required to keep the flat plate fixed. And as we did for the heat transfer coefficient, now we use the Nusselt number to non-dimensionalize. Here we can also non-dimensionalize the wall shear stress. So tau wall, the wall shear stress, divided by 1/2 rho u infinity squared. Then we find a formula for the skin friction coefficient. And in general, this depends on the position over the flat plate. So we have now clear in our mind what the velocity boundary layer looks like. In the same way, we can define a thermal boundary layer. So for the velocity boundary layer, we define the region near the wall where velocity gradients are important, whereas in the thermal boundary layer we define it as the region near the wall where temperature gradients are important. So we can sketch it here in two ways. For example, if you have a cold flow over a hot plate, then we will have temperature profile of this sort, and we indicate the thermal boundary layer and its thickness by delta T. Instead, if you have a hot fluid flowing over a cold plate, then the velocity distribution will be of this form. So as I said, the thickness of the thermal boundary layer, we can now call it delta T. And we define it mathematically as the distance from the wall where the temperature difference T, the temperature at a certain location Y, minus Ts, the temperature of the surface, equals 99% of the difference between T infinity and Ts, where T infinity is the temperature of the fluid far away from the wall and Ts is the temperature of the surface. In the same way as the velocity boundary layer grows as we move downstream, also the thickness of the thermal boundary layer grows as x grows, because heat transfer effects are felt at a greater distance from the wall. So as we have a flow that over a flat plate, we have temperature gradients and velocity gradients, so the velocity and thermal boundary layers exist simultaneously. In general, they have also different thicknesses. And also, in the most general case, the velocity field and the temperature field are coupled. So to solve a convection problem in general, we will have to solve for the velocity field and the temperature field at the same time. More information about the two boundary layers can be extracted from a non-dimensional number called the Prandtl number. This Prandtl number is a non-dimensional number and is defined as the ratio between the diffusivity of momentum due to viscous effects and the diffusivity of heat. So mathematically, the Prandtl number is defined as the ratio between the kinematic viscosity and the thermal diffusivity. We can also write it in this way as mu, the dynamic viscosity, times the specific heat divided by the thermal conductivity. So what does the Prandtl number actually represent physically? First, we have to remind ourselves the physical significance of the kinematic viscosity. So the kinematic viscosity of a fluid tells us how quickly momentum diffuses because of viscous effects. So for example, let's take the case of a plate that is suddenly put into motion in a still fluid. And at different times, we can sketch the velocity profile. Initially, all the velocity gradients are confined very close to the wall. And as the time progresses, then viscous effects start to diffuse upward. And so we have a thicker and thicker region where velocity gradients are important. So the faster this process occurs, the larger the kinematic viscosity. So there's a strong analogy with the thermal effects, because we already discussed this about the thermal diffusivity. Thermal diffusivity of a fluid or also of a material tells us how quickly thermal effects diffuse. And we already discussed this when we studied the semi-infinite body problem. If you remember, we suddenly changed the temperature of the surface. So from an initial temperature Ti, we increase the temperature to infinity, and we observe that the thermal effects diffuse and time progress. So more and more heat transferred through the body, and so the particles inside the semi-infinite body felt the change of boundary conditions. So there's a strong analysis between the effects momentum diffusion due to viscosity, kinematic viscosity, and thermal effects, diffusion of thermal effects due to thermal diffusivity. The other important thing to note is that the kinematic viscosity and the thermal diffusivity have the same units. That's meters squared divided by seconds. So the Prandtl number, being the ratio of two quantities with the same units, is non-dimensional. So it tells us how fast does viscous effects diffuse with respect to thermal effects. So this is true also for flow over flat plates. So although the Prandtl number is of course related to properties of the fluid, it tells us a lot about the convection, and we will study this more in the next lessons. There are two cases that are worth reminding ourselves. One is about when the Prandtl number is much smaller than 1. In this case, heat diffuses very quickly, so the case, for example, liquid metals. Whereas instead the Prandtl number is much larger than 1, viscous effects diffuse very quickly, for example, in lubricating oils. Air has a Prandtl number of about 0.7, so when the Prandtl number is about 1, we usually have gases. And the Prandtl number of water varies between about 1.6, 1.7 to up to 13, depending on the temperature. And of course, we also need to remind ourselves what the Reynolds number is. Reynolds number is a non-dimensional number. It's a ratio between inertia effects and viscous effects, and is written as defined as the ratio between the product of density, characteristic velocity, and characteristic length divided by the dynamic viscosity. But the dynamic viscosity divided by the density equals the kinematic viscosity. So this is a more compact way to write the Reynolds number. So when the Reynolds number is large, then inertial effects prevail, so the flow has more tendency to become unstable and to develop into turbulence. Whereas instead the Reynolds number is very small, for example in microfluidics, then viscous effects dominates, velocity are usually small, the length scales are very small, so the flow is likely to be laminar. And in most cases we can define a critical Reynolds number. That above this critical Reynolds number we have a turbulent flow. So all these concepts are very useful to study heat convection. Thanks again. I see you in the next video.